This is your last lecture on commutative damage on fatigue. The topic is commutative damage. For many type of structures, what you really have is you have a case scenario in which you have many different type of cyclic loading, and they're repeated many different times. Okay, and what you want to do is you want to find a way to know if there's actually damage occurred with many different cycles. Um, so basically what you want to do is to understand how this actually works, we're going to call small n the number of cycles, the sequence, number of cycles sequence that sequence is repeated. Okay, so in this example, let's say n1 for an example is equal to, so from this plot, what you do is you count how many times the cycle repeats. So it's 1, repeats 1 time, 2, 3, 4, 5 times. So this cycle repeats 5 times. So n small will be 5. And 2, then you repeat again, you count how many peaks you have, right? This is easy to count, but in real life, you don't have something like this. It's way, it's way more scattered. So what you will do is you just know how many cycles of each these cycles repeated, and for each one of those cycles, in 3, it can be maybe 10,000. It can be any number. How many times this sequence is completely repeated. Now, at the end goal, what you really want to do is is basically solving the problem many times. First of all, the structure will be exactly the same. So the structure is same. Since the structure is same, your SC diagram, your endurance limit will be the same, your SN diagram will be the same, your fatigue diagram will be the same, right? So these plots are identically the same because all I'm changing here is structure. All I'm changing is the loading sequence. Since I'm changing only the loading sequence, these plots remain the same. All I want to find is your sigma alternate, your sigma mean for each one of these cases. So let's say here, and from here, I will find what my SA is, SM, and note that this one, the subscript 1 doesn't refer to principal stresses, but refers to the loading sequence, okay? And then from here, I want to find my sigma, your equivalent Goodman stress, and from here, you find what is the life of the structure, okay? And just remember that what we did this, we're going to solve this for many cycles. Each one of these cycles is going to have its own, your own n. If you are here, then your life cycles are infinite. If you're here, you got finite life cycles. Okay, so so basically, this is what you really want to do is, and then you want to repeat this many times. You repeat this for this loading sequence, repeat for the second loading sequence, and you keep repeating this many sequences. Another thing to keep in mind, what we typically do, this is what we may call a block cycle. This is one block. So in the test data, you may get all these different cycles that you have, and that's one block cycle. At the end of the day, you can really have maybe 3, 4 block cycles. This is repeated 10 times, 100 times, 1,000 times, and that can be a whole block cycle, okay? And another thing to keep in mind here is realize that this particular theory that I'm going to discuss is a linear theory. So if there is a damage that started here, this point will now know that damage occurred there. So we just talked about damage as a complete set. There are other theories that do take damage in each one of the, so if I'm here, what happens there takes, if there's any damage in the previous state, it actually takes that into account, but that's beyond the scope of this course. So your theory then basically is going to be equal to the following equation. This is the famous Pilgrim's equation. So there's a BF missing here. Okay, and BF again is the block cycles in my problem. This is the damage parameter, and the damage parameter has to be less than 1 to be safe, has to be equal to 1 to be onset of failure, hasn't failed yet, and onset of damage actually. And then bigger D, that means the damage has occurred. Okay. So, and if this is less than 1, then basically what you have is your N equivalent, your number of cycles equivalent will be 1 over D, and that will be how many cycles, equivalent cycles, your structures really has remaining. Okay. Anything beyond this means that it's damage occurred. That means that you really have finite life. Okay. And so if you take the inverse of this, you will see that you get less than 1 cycles. So that means that that is really not acceptable. The way you work these problems out is, let's say, just for an example, maybe your first sequence is 5,000, and then your N from your SN diagram coming from here, you find your loading sequence, and then you come here, you find this, and you will find this is 10 to the 4, plus this is 10,000. I'm just hypothetically, maybe this is infinite, and then you can just keep on going, and maybe there are 5 block cycles that are left in the problem. Okay, then this will actually give you a number. Okay, that's the number that you want to check. Now, I do tell you then at least in the aerospace industry, when we have a data, right? We have a spectrum, or we can either model that, or we have the test data or something. We only have this data we want to keep on using. It may look something like this. So what we did, this is one life of my aircraft. Okay, one life. So you may have many block sequences, maybe block 1, block 2, block 3, block 4, and maybe all those blocks equal to 1 life. And typically what we do is we actually use a scatter factor of 2 or maybe 3, and sometimes even up to 4. By scatter factor, we mean we will repeat this whole sequence that many times. So if this was actually had maybe had 1, 2, 3, 4, 5 blocks, and I wanted to have a scatter factor of 2, then I would, in addition to this, multiply 5 times 2, and that would take care of my life cycle. So that's typical in the industry. That's what we do, and that completes our discussion on theory of commutative damage.